Hello, my name is Haaris.
My name is Friedrich.
My name is Han, and our idea for the Imperial Science Competition is improving UAV efficiency with retractable fixed wings. There are two main types of UAVs, fixed wings and rotary wings. Fixed wings need to be moving forward constantly, so they require a large runway for takeoff and landing, which may be impractical. Rotary wings are very precise and can fly directly upwards. However, they require quite a lot more energy compared to fixed wings, making them inefficient. We aim to make a retractable fixed-wing drone where the fixed wings can be stored during landing, takeoff, and tight maneuvers, and the wings are utilized in long-range trips to reduce the power output required. We aim to take the benefits of rotary wings for takeoff and landing to create essentially a more efficient long-distance hybrid drone.
We aim to combat goals 9 and 12, with our innovation lessening the power output for drones and thereby reducing the energy consumption over time. We achieve this by lessening the reliance on the rotary wings so you could reduce the power output and the speed they would rotate at, as the wings would provide the lift instead of the rotary wings, and therefore the drone could last longer in the air. For us, we mainly see the use of our technology within the delivery industry and potentially farming methods. We aim to scrap traditional fuel-consuming CO2 emitting vehicles and replace them with our drone technology. After assessing the main issues with rotary wing drones and their poor long-distance efficiency, we set to locating where the problem lies in most of these drones. We ran a series of simulations on DJI Phantom 3 CAD models through SimScale to test their aerodynamics. As you can see in the first image, there was flow separation when the air came in vertically, showing the inefficiencies lie in the body of most of these drones. As we toggle to the second image, this highlights flow separation even better and the reliance on the rotary powered wings to produce lift. Lift can only be created with perfect airflow and a clear pressure difference, which I'll explore in the latter slides. This third and final image shows a near perfect airflow from our simulations for a regular fixed-wing drone. This is a pressure simulation of a DJI drone. The downward arrow likely indicates the direction of the thrust or airflow generated by the rotor blades. The difference in pressure with the blue areas on top of the rotary wings and the red below highlight the pressure difference, which is so key to generating lift. This simulation really shows the reliance on the rotary wings to produce the lift. As you can see, the main body of the drone is completely blue, showing that there was no pressure difference, highlighting the need for our project in creating a drone that can create lift from wings.
The current existing designs are all limited and don't quite fit the objectives we have defined for ourselves. However, the image on the left has a folding mechanism that we do want to take inspiration from. Our next step is to find the appropriate mechanism and start the modeling and mechanism process.
In this example, the wing would rotate by 90 degrees, causing the UAV to easily switch between the more agile rotary wing drone and the more energy efficient fixed wing drone. Here, the wing surface could be made up of lots of small strips of material, meaning the wings can be completely folded together. A servo motor can then be used to change the angle of the wing, which changes the angle of attack.
I developed the code for the Arduino board in C++. The code was fairly simple, and after some trial and error, I found the correct angles to use.
This is our first prototype, made out of cardboard, servos, some hot glue and an Arduino. Here you can see the folding mechanism, which works really well.
We've yet to optimize our angle of attack fully, but if we progressed, we'd optimize the angle of attack for 3 scenarios: cruising flight, high-speed flight, and tight maneuvers. Here we have our original wing design, but we've added another servo to develop a mechanism to change the angle of attack with the potentiometer, which uses resistance. The code was initially tricky to develop, but after a few hours we finally got there. The wing cross-section is designed to be adaptable to a wide range of wind speeds. We have also gone for a medium aspect ratio, as it provides good lift and has good low speed characteristics. By utilizing a 3D printer, this shape is very time efficient to print and takes up little space on a printing board.
After downloading the 3D model for a DJI Phantom 3 drone, we set to developing the final model. Mechanism-wise, you can see that we decided to go for a single fold in the wing, as this strikes the best balance between the drone being compact and the folding mechanism being reliable. Overall, the CAD modelling process was quite extensive, as we made the model fully functional with moving joints. However, we felt it was very rewarding, as we learned a lot of new skills from the experience, and it helped us to better understand how to actually build our design. In the top video, you can see how the wing folding mechanism works. In the bottom video, you can see how the changing of the angle of attack mechanism works. Here is a high quality rendered image of our final 3D model, and this is what we hope to build.
Our innovative drone design incorporates an adjustable angle of attack with fixed wing, optimizing lift and minimizing risks of wing stalling during flight. This approach enhances lift efficiency and coupled with foldable technologies, introduces a novel and practical dimension to drone engineering. The integration of these technologies is aimed at preventing wing stalls, a critical factor in sustaining optimal battery life during drone flight, as illustrated in the accompanying images on the left.
For the 3D printing process, we used PLA. All parts are printed with this filament because it's cheap and quite rigid. As we designed the parts with a focus on 3D printing, for example flat surface on the end of the wing, meaning 3D printed parts had good adhesion to the build plate, and no large overhangs, meaning minimal support was necessary, the parts printed quite fast with few issues. In the future, we may change the design to optimize it even more for 3D printing. For example, this could include making the inside of the wing hollow, meaning it will print even faster and also be lighter.
Putting the drone together was a tricky process that required soldering for the lever and zip ties to attach the 3D pieces to the drone. This is the drone after being fully assembled without the electrics. As you can see, the wings droop down slightly. The support of the wings is likely to be changed in our next design if we progress further. Here is a video of our drone in the air, along with the angle of attack mechanism being operated with an infrared remote that I coded with Arduino. I coded 4 buttons, 2 to change the angle of attack, and 2 for the folding wing mechanism. Here are some different clips of the folding mechanism working. From our results, we posted a 5% increase in the time spent in the air, which is very impressive. However, looking forward, we hope to scale up the drone to see better results, and if we develop this even further, we would like to have everything a little bit more integrated. We would perhaps change the wing design to retract in more and create a specialized case for electronics. We'd also love to add some kind of solar design panel if we can. Thank you very much for listening. Sorry we went slightly over the time, but we hope to progress further as we've really enjoyed the competition so far and we'd love the chance to develop our work slightly further.